last theorem. So first of all, note what is the extension of a, so given f from D to R, let D be a subset of E. What does it mean by an extension? So the extension, then the extension of f to from D to E is a function f tilde, just we are giving it a name, to R such that basically f agrees, f of x equals to f tilde of x is equal to f of x for all x belonging to D. Okay, so this is what then extension means. So you have this set D. So suppose let's take D to be this set 0, 1. So let this set be D. Yeah. And now what is an extension of this function? So suppose f of x equals to x squared. Now you're extending it to a bigger set, say -1 to 2. And this is an extension if what happens if f tilde of x equals to f of x on 0, 1. Yeah, how the defined outside 0, 1, it doesn't really matters, right? I mean, then this becomes an extension. The only thing is that it should agree, this f tilde should agree with f on D, which is 0, 1. Okay, so this is what it means by an extension of a function. So uniform continuity basically lets us extend our function in the following way. So theorem. This is theorem 5.4.9 from the text. It says the following. If we take a function from AB to R, which is uniformly continuous, yes, on AB, if and only if we can extend, it can be extended to a function f tilde. So you're extending it, so it has to be a bigger set. We are not being greedy. We are only extending it to the boundaries of this to R. And what is the property of this f tilde? F tilde is such that f tilde is continuous on AB. Okay, so let's try to understand the significance of this. So if you have a uniformly continuous function on an open interval AB, then you can extend it to a continuous function, to a function, continuous function on closed interval AB. And it is if and only if. If you can extend it as a continuous function, then the original function must be uniformly continuous. Okay, so let's see the proof of this. So proof, but before we go for the proof, let's look at an example where this doesn't work. So let's take f of x equals to 1 over x, right? On say 0, 1. Now this function, clearly this function is not uniformly continuous, is not uniformly continuous. All right, it's not hard to prove. If you want to prove it, you just basically choose so 1 minus x. So if you want to prove this in this that it is not uniformly continuous, take 1 minus x 1 minus y, which is your f of x minus f of y, and then you'll get x minus or y minus x, which is same as x minus y divided by xy, right? And then what you do is, no matter what your x minus y, if you take x minus y, so you want this to be less than epsilon, right? But you can choose x and y close enough to 0 that this whole thing will blow up and it will never get less than epsilon. Okay, so So this could be a good homework to check that f of x equals to 1 over x is not uniformly continuous. Okay, right. So this function is not uniformly continuous, and hence you can see that you cannot extend it to, you cannot extend it to 0, 1, right? There's no extension, extension which is continuous. The continuous part is important. Of course, you can extend it to whatever function you want, right? I mean, like you can have, say, you can extend it. So one here you can say, okay, I'll define it to be this value. So it's not that the extension is impossible. You can always extend any function, but the continuity of the extension is important. Okay, so let's look at a proof of this. You'll say, well, what's the use of this? Later on, you will try to have sequences of function, and there the domain becomes important. All right, so yeah, so you will see that in maybe analysis too. Okay, so let's see the proof of this proof. So suppose, so we have to prove both ways. So let's say f tilde, suppose f tilde, there exists f tilde from AB to R is continuous, or on, well, let this be continuous. So this implies f is uniformly continuous. Why is that? Because we already saw this theorem. The theorem was 5.4.6 of the text, which said if f is a function from D to R, continuous, and D is compact, then f is uniformly continuous. Right? So let this be continuous. Therefore, f is uniformly continuous as what? AB is compact. Yeah. So if you're continuous on a set, then you are continuous on a subset of it. Therefore, f is continuous on, sorry, f is uniformly continuous on AB. Okay, so I'm using the following fact. If f is continuous on a set, then it's going to be uniformly continuous on the subset of it, right? All right, so the next part of it is the following. So now you have f is uniformly continuous. So conversely, f is uniformly continuous on AB. Show that f tilde, show that there exists extension f tilde of f on AB, which is continuous. Okay, so how do we go about it? Well, so consider, so f is uniformly continuous on AB. So consider a Cauchy sequence converging to A. Let's call this Cauchy sequence as Xn. Yeah, you can always construct such a Cauchy sequence, right? So consider Cauchy sequence converging to A. This implies f of Xn is a Cauchy sequence in, so consider a Cauchy sequence converging to, Cauchy sequence in AB converging to A. Yeah, so f of x is a Cauchy sequence in R converging to converging to what? We'll come to that in a minute, but note that we did a problem in the last class where we had an example of a function which was not uniformly continuous, and you had a Cauchy sequence which was divergent. All right. So here we have f of xn is a Cauchy sequence in R, right? And so every Cauchy sequence in R converges in R, all right? Not converges in the f of AB, but this sequence is going to converge in. So the Cauchy sequence in R, and hence is what? Hence, so converges in R, right? So let f of xn converge to P. Yeah. So xn converges to A, but f of xn converges and f of xn converges to P. All right. So we actually moved to R when we are talking about the convergence of it. So now what you define is the following: let f of A be P. Now claim limit as xn goes to infinity of f of xn is clearly P, right? But coming from the sequential continuity point, we have xn converges to A, we have f of xn converges to P, which is my f of A. Yeah, so I should have defined this as f tilde, f tilde. So I have basically uh, xn converging to A, but f of xn converges to f of tilde of A. So, but what did we wanted to prove? We wanted to prove that f is uniformly continuous. We wanted to define f tilde, right? So so we defined f tilde of A is P, and f of x equals to f tilde of x equals to f of x on AB, right? So this is our extension. So, and also similarly, we have let yn converge to B. So we'll have, so yn converges to B in AB. So this means f of yn, so this means yn is Cauchy. Yn is Cauchy. This implies what? This implies f of yn is Cauchy. Why? Because f is uniformly convergent. So yn is Cauchy in R, and hence f of yn converges to Q, and then you define this new function f tilde on closed interval AB to R, and define basically f tilde of A equals to P, f tilde of B equals to Q, and f of x, f tilde of x equals to f of x. And then you can show that this f tilde from AB to R is continuous. Yeah. So how do you show the continuity? You can show continuity using the fact that using the fact that it's a Cauchy sequence and Cauchy sequence converges. So you have shown using sequential continuity. So for example, let's investigate this one, and then you can do the second one the same way. So we have let xn be any sequence converging to A. Then we have f of xn converging to basically what? Converging to f of f tilde of A, which is P. And now this sequence is same as f tilde because all these xn's are in AB. So f tilde converges to tilde of A. because xn was any sequence, so therefore f is continuous, f tilde is continuous at A. Similarly, you can work for B and therefore you prove your result. Differentiable at point C. So differentiability or the concept of derivative. So note that for differentiability now you have to come back to the functions of to come back to real valued function, all right? Or a function, a multi-valued, sorry, real valued function or a function whose outputs are tuples, but those tuples have to be real numbers, okay? So what is the, so let's take a function f from say interval I to R, where is differentiable at C belonging to I if limit as x going to C of f of x minus f of C over x minus C exist. Okay. So whenever this limit exists, we say the function is differentiable at C. Okay. So with this exists, and of course on top of it, since we talk about infinite limits as well, we'll say n is finite. And we'll denote this by f prime of C. Okay. So now again, like continuity at a point C, it's a local phenomena. Differentiability is also a local phenomena, right? It's about a point really. However, you can extend it to a set. So let D be a subset of I. We say f is differentiable on D if f is what? Differentiable at C belonging to D for all C. Yeah, so if it is differentiable at every point inside, then we say it is differentiable. All right. So again, the motivation is, of course, the motivation lies that the existence of the slope of the tangent line and so on and so forth. But that is not our concern at the moment. So consider the following example: f of x equals to x squared. Now, if you look at for any C, let C belong to R be arbitrary. You can see that f prime C is going to be limit as x goes to C of f of x minus f of C divided by x minus C. This is going to be limit as x goes to C of f of x minus f of C, which is going to be x squared minus C squared upon x minus C, which is going to be limit as x goes to C of x plus C divided by x minus C over x minus C. And in the limit game, you can cancel this off, so you get 2C. Now, this limit, so therefore this limit exists and is finite. Therefore, f is differentiable. So this is true for all C belonging to R, right? So therefore, f is differentiable on R. Okay. So that's the idea behind the differentiability. All right. So yeah. So now you can convert the same. So now we have all the tools and discussions from the limits, right? Which we can transfer over here. So namely, we can have the following theorem. So 6.1.3, which says that let f be from I to R. So I is fixed for interval. Okay, so I is an interval. It's a fixed interval. We are discussing about an interval. So let f be a function from I to R, and let C belong to I. Then f is differentiable at C. If and only if. So now we want to give the sequential criteria for the differentiability, and that sequential criteria can come from the definition of limits. So if and only if for every xn in I, note that we pay importance to this because all the sequences should be well defined, right? So for every sequence xn in I with xn converging to C, we have what? Of course, with xn not equal to C, we have this sequence f of xn minus f of C over xn minus C converges. So again, we just restated the definition in the following sense. We basically said, well, I mean, instead of taking the limit, we are now talking about the sequential criteria for differentiability. See, the sequential criteria is important because it helps you. Generally, it may be easy. It's not as easy to use sequential criteria to prove continuity or differentiability, but it's easier to disprove disprove that function is continuous at a point using sequential criteria. Okay, so let's move ahead. Furthermore, this sequence converges to f prime C. Okay, so there are a lot of things at the background that the limit of this sequence converges, and therefore the limit is unique, and that limit is f prime C. Okay, so let's see how the sequential criteria can be useful. We'll use this to disprove differentiability at some point. So let's take an example again from the text. Take f of x equals to x to the power absolute value of x, right? Then what do we have? We want a sequence. So let's take a sequence. So we know that this is not differentiable at 0 from whatever we learned in calculus 1. So let's try to prove that using, now we'll use sequential criteria. So let's take xn equals to minus 1 to the power n over n. You will say, why are you choosing that? Well, notice that if you are only coming from one side, then there's not really a problem. Yeah, you have to basically oscillate between here, and then you basically show that the limit will not exist because it will depend on which path you are coming from, right? So this is what I'm going to do here. So xn, now you can see that xn converges to 0. But what about f of, so you see that xn will converge to 0, but what about f of xn minus f of 0 over xn minus 0? What about this sequence? Let's see. So this sequence is going to be, f of xn is going to be 1 over n minus 0, because absolute value of this, the minus 1 to the power n will disappear, over minus 1 by n to the power n. And this can be seen as 1 by n divided by 1 by n times minus 1 to the power n, which is minus 1 to the power n, which basically diverges, right? So you see, using sequential criteria, you are able to show that you have an xn converging to 0, but this sequence diverges. Therefore, we get that f is not differentiable at 0. Okay, so there's no differentiability at 0. So to show that this is not differentiable at 0, it's not differentiable. We are already, we have some idea from calc 1 that this is not differentiable, because if I try to use this formula, I'll see 2 by 3 x to the power minus 1 by 3, and at 0 it's not defined, right? But however, we want to prove it purely from the analysis point of view. So let's see. So let's take an xn converging to 0. And again, as you said, we want a pretty xn. So let's take this pretty xn could be take 1 over n. Let's see. So even the previous minus 1 to the power n will also work, but let's take 1 over n converging to 0. Yeah, this is my xn. I'll see if we need minus 1 to the power n there. So let's see. So what is, so xn converges to 0, but let's see f of xn minus f of 0 or xn minus 0. So this is going to be 1 by n to the power 2 by 3 minus 1 upon, sorry, f of 0 is 0, right, over 1 by n minus 0. So we get 1 by n to the power 1 by 3. And that goes to infinity. No, my bad. That goes to 0. All right. So see, this one did not really work because I had 2 by 3. So what I'll do is I will again go back to the technique of minus 1 to the power n. So again, I'll come from both sides now. Minus 1 to the power n. Then I will have, so in that case, I will have minus 1 by n, sorry, minus 1 to the power n, the whole power 2 by 3. Okay, minus 1 to the power n. So I'll use minus 1 to the power n here as well. Then what do we get? We can basically see that in the top you're squaring, so minus 1 will disappear really. Although you're taking cube root after, but it still disappears. So you'll have 1 by n to the power 2 by 3 on the top. In the bottom, you have 1 by n over n, and that will be minus 1 to the power n over n to the power 1 by 3. Yeah, and that basically also converges to, this converges, right? No, that is correct. So it converges to 0. In this case, you will get 1 by n to the power 2 by 3 minus 0 over 1 by n minus 0. And as you guys rightfully said, this is going to be 1. This is basically multiplying by the reciprocal of this guy. So this is going to be 1 by 1 by n to the power 2 by 3 multiplied by n, which is n to the power 1 by 3. And this goes to infinity as n goes to 0. So it diverges to infinity. Okay. So there are two notions, right? Diverging to infinity, not convert, divergent itself, and diverging to minus infinity, right? So when you say it is divergent, you're not saying whether it is oscillating or going to infinity or minus infinity. But diverging to infinity means it's going to infinity. All right, again. So therefore f of x is not continuous at x equals to 0. All right. So this takes care of that. Now another question. Take f from R to R. Take f of x equals to, this is an interesting question, you should try it. Whoa, what's wrong with my computer? Oops. Okay, sorry. All right. Okay, so f of x is not continuous, so is not continuous at x equals to 0. Now let's move on to the next example. So it's a good exercise. Take f of x equals to exercise. Take f of x equals to x sine 1 over x if x is not 0, and what 0 if f of 0 if x equals to 0. So first of all, this function is continuous at 0, and then you have to argue whether it's differentiable or not. Okay. So you saw in the previous example that this guy is continuous. This guy is also continuous at 0, but not differentiable. So this basically leads us to the following theorem. So f is differentiable at c belong to I. So if this function is differentiable, then f is continuous. So proof. So what do you want to show really? You want to show that limit as x goes to c of f of x equals to f of c. Yeah. Why are we using basically the limit criteria? The reason for that is c is in I and I is an interval. So every point is an accumulation point. Okay. So there's no problem in using the limit criteria for the continuity. So define the following. Let f of x be f of x minus f of c over x minus c plus f of c. And then you multiply it with x minus c. So consider this function, and this function is defined for x not equal to c. Yeah. Now look at the limit. So what is limit as x goes to c of f of x? Now each of this limit exists, right? This exists, well, this limit is 0. This limit exists because the function is differentiable. So we should write that since f is differentiable at c, limit x goes to c of f of x minus f of c over x minus c exists and is finite. Let's call it. So let's call it what? F prime c. That is f prime c exists. Okay. Now in this case, we'll have limit as x goes to c of x minus c times limit as x goes to c of f of x minus f of c over x minus c plus f of c. So this limit is going to be 0. This exists times 0 plus f of c, which is going to be f of c. So therefore, f is continuous at c. So therefore, f is continuous at f is continuous. Note that you cannot blindly use this definition. All right. So the limit definition only is valid if what? If you can get c as an accumulation point, right? Okay. All right. So let's move on ahead. So now there is an algebra of differentiability, namely the following. So if you have, so theorem, f, g are function from I to R are differentiable at c belonging to I, let k belong to R be a constant, then the following functions are differentiable. So what are the functions which are differentiable? K, f, f plus g, f by g, and k, f minus g, of course. So these functions are differentiable. All right, so you can also think about a vector space of a differentiable function, and you can think about linear operators there and so on and so forth. So, and not only that, we have certain results for them. So what are the and on top of that, we have that kf prime of at C is basically same as k times f prime of C. Then we have f plus g prime of C is going to be f prime C plus g prime C. Second, we have f g prime of C is going to be f prime C times g of C plus f of C times g prime of C. Then what else do we have? We have f by g of prime of C is going to be g of C square g of C times f prime C minus what? F of C times g prime of C. Of course, here the extra condition we need, that is provided what? G of C is non-zero. Okay, so these are the formulas for differentiability. And how do you prove it? You can prove it the same way. All right, so yeah. So, well, you can use the limit criteria. So for example, I want to prove this one, then I have f g prime at C is going to be limit as x goes to C of f g of what? X minus f g of C divided by x minus C. But what is f times g of C? By definition, that is going to be limit as x goes to C of f of x, g of x minus f of x, f of C, g of C divided by x minus C. And now I need to manipulate this. So this is already the derivative, but I need to manipulate it to make it look like, so I'll take f of x, g of x. Now I will subtract and add. So let's say first one, I want to have f prime of C. So what I'll do is I will basically take g of x times f of C, add and subtract this guy. So I get g of x f of C minus f of C, g of C, and then divide whole thing by x minus C. Then I'll take, this is the usual you saw in your calc course as well. Take g of x common, so we'll have f of x minus f of C divided by x minus C times g of C plus, here I can take f of C common, so I'll have what? I'll have f of, sorry, g of x minus g of C divided by x minus C. Now, given the fact that this limit exists, right, because we are saying it's differentiable, note that these formulas do not apply if the functions are not differentiable at that point. All right. So this is going to be f prime C times g, limit at x goes to C of g of x is going to be g of C because it's continuous. And this is going to be g prime C times f of C. So similarly, you can prove all the other ones as well. So now let's move ahead. And so I know that